In this lecture, we're going to build a slightly more useful coroutine type, and this is going to be a generator that is going to be generating numbers lazily on the fly. And we want our coroutine to work like this, so we're going to set up a coroutine type and set it as the return value for our coroutine function. This is the setup we have grown to know and love. And inside we're going to co-yield. So the first time we hit the body of this function, we're going to pause and yield a 10. And if we resume this, we're going to pause here and yield a 20. And if we resume again, we're going to yield a 30 and pause the coroutine. And if we resume, we're going to make this coroutine run to completion. So if we call this 3 times, we're going to generate 10, 20, and 30. This is the setup we want. Okay, so we already know that in C++20, what we have is the coroutine infrastructure. And if we want to use coroutine types like a generator, we either have to build one ourselves or we have to use third-party libraries. In this lecture, we're going to build our own and use it to generate numbers lazily on the fly. And it is not going to be something you haven't seen already. So this is going to be our generator coroutine type. The name is going to be generator. And to make this a proper coroutine, we need to nest in a promise type class. This is what we do here. This promise type is going to be wrapping around a value that we will be yielding. And then down below, you see that we have a bunch of helper functions. We have a generator constructor, which is going to construct a generator from a promise type. And you see that in our initializer, we are grabbing the coroutine handle from the promise and using that to initialize our coroutine handle member variable. Nothing complicated here. If we go in our promise type, we're going to see that it is nothing we haven't seen. We have our member functions here. We have get return object, initial suspend, final suspend. We have our exception method, and we have a yield value method because we are really interested in yielding values from our coroutines. So we don't really care too much about return void here, but we want to put this in case we hit the end of the coroutine and the compiler calls return void here implicitly. So this is a safety mechanism we are playing here. Now, we want this generator to be called using the function call operator. And what we want to happen is to resume the coroutine and return the value to be used by whoever called this function here. We are going to achieve this by setting up a function call operator in our generator. That's going to make this guy a functor because we can call its objects like we call functions. And what that's going to do is to resume the coroutine and return the current value to be used by whoever happened to call this operator here. And this is really all we need to do to get this generator to generate numbers lazily on the fly. Now, once we have this, we can set up a bunch of coroutine functions that are going to return our generator coroutine type. Because it is a class template, we are going to create template instances for whatever type we want to generate. In this case, we want to generate integers. The first one is really what we have seen. We are going to co-yield 10, 20, and 30. But the second one here is going to generate an infinite stream of numbers. So we are going to start from whatever number we specify as our starting point here. And we're going to keep incrementing and yielding values. And if we co-yield, the coroutine is going to pause. And next time we call it again, we're going to print our incremented value as a result of the code that runs after our co-yield statement here. And we're going to keep generating numbers, for example, 1, 2, 3, 4, all the way to even 1 billion if we allow our program to run up to this point. So this is what we are up against in this lecture. We are going to head over to Visual Studio Code and actually do this. Here we are in our working folder. The current project is custom generator. We want this to be based on what we did in the last lecture. So we're going to copy the code from there and use that as a starting point in this project here. And we are going to crack this open in Visual Studio Code by dragging and dropping here. This is going to give us a main CPP file that we can use as our starting point. And we want to remove anything below. And we're going to go in the main function and remove everything because we want to somewhat start from scratch here. So we remove everything and we keep in the done statement here. And we will have our coroutine type. We are going to change this to be a function template. So let's say template. So this is going to be a function template. We're going to change our value to be an instance of our template here. And we're going to change the parameter for yield value here to be of type T. We want to keep in return void, but we don't want return value here. So we're going to remove this. We also want to change the name of this class to be generator because this is going to be our generator. So let's make this generator. And we're going to change this throughout the entire class here. So here we're going to return generator, and we can go down and change our constructors to say generator. I think these are the only places where we need to change this. And I don't think we have any other place where we need to change this. Here we need to return generator. I think this is the place. And let's pass this through the compiler to see if we don't have any boo-boos in here. So we're going to pass this through GCC, our favorite compiler, and we're going to see that the build is good. So this looks like the code is going to work just fine. We have everything in place. What we really need is our yield value method to yield numbers lazily as we loop through our generator, or our coroutine, I should say. But what we need is a function called operator that is going to allow us to call methods on objects of this coroutine type. So we are going to go in front of our coroutine handle, and we're going to put in our function called operator. Let's do this. This is going to return T, whatever type we are storing in our promise here. And then we're going to say operator function call, and we are going to assert and see if our handle is pointing to something. If it is, we're going to resume the computation, and then we're going to return our value to be used by whoever happens to call our coroutine here. Now, once we have this coroutine type in place, all we need to do is to use it in coroutine functions. I am going to put in 3 coroutine functions using our coroutine type, which is generator. The first one is going to generate numbers, and we are going to call yield 10, 20, and 30. You recognize this example already. We have seen this a lot of times. The second one is going to generate an infinite number stream. So we're going to start from 0, for example, and we're going to keep incrementing, even hit 1 billion if we allow our program to run up to that point. The last one is going to set up a range of values. We're going to have our boundaries between first and last, and we're going to print numbers between this range. You see that we have a while loop, and we can grab numbers by looping through this range and grabbing values by resuming the coroutine. You're going to see how this works in a minute. So let's try out the first one here. So we're going to set up a task. We can go down and do that. We're going to say auto task 1, and it is called generate numbers. I think this is the name of our coroutine. Let's go and see if this is the case. And at this moment, the coroutine is going to pause on start. So it is going to pause at this location here and wait to be resumed to actually run code in the coroutine. So if we resume this, we are going to use our function called operator. Let's name this task 1 to make things easier. So we're going to say stdc out, and we're going to say value, and we're going to say task 1. And we're going to call our function called operator on this little guy. And we're going to see that this is going to resume our coroutine. And it is going to print this message here. And it is going to call yield 10 and pause at this point. This is what we are going to see. Let's pass this through the compiler. And we will see that we need to include cassert for this to work. Let's go to the top and do that. And we are going to build again, pass this through GCC. One thing you should notice again is that we are passing an option to use coroutines in GCC 10 here. If you don't do this, you will get a bunch of compiler errors. So make sure you have this in, and your code is going to compile just fine. Now, we will have our binary generated. We can bring up a terminal window. If we do ls, we're going to see our binary right here. So we can run it. Let's clear and run Rooster, and we will see that this is going to print our value, and our coroutine is going to pause. You will see that we are going to pause at this point here. And next time we run this, we are going to resume from this point. We're going to print the message on line 50. We are going to call yield 20, and we are going to pause our coroutine at this point right here. So let's resume again. We're going to print the value again. We can go in the main function and say stdendl to separate these things. And then we're going to print our value again. I think we can do something like this. And we are going to call the function call operator on our task object here. This is going to resume the coroutine and print our value because we are returning this value from our function call operator, as we see right here. So let's pass this through our compiler. We are going to use GCC again. The build is good, so let's clear and run rooster. We will see our value 20. And we can resume again. Now you are probably getting a hang of this. So we can grab this and copy and paste it one last time to hit the end of our coroutine. So let's do this. And if we print again, we're going to see the 30 printed out because that's what we're going to call yield and pause the coroutine. The build is good, so we can clear and run rooster, and we will see that our code is done. The value is 30. But at this point, if we ask our coroutine if it is done, it is going to say it isn't done because we are paused at this point here. Let's make sure you see this. So we are going to ask the coroutine, are you done? And we are going to say it this way. We're going to say coro done, and we are going to say task 1, handle and done. And this is going to print and tell us if the coroutine is actually done. Let's go to the top and say std cout and say std bool alpha to see this in the form of true and false. And we expect the coroutine to say that it isn't done yet because we know that it has just paused. So if we run rooster, we're going to see that the coroutine is not done yet. But if we resume it again, we're going to see that it is now going to run to completion. We are going to see these messages here, and the coroutine is going to run all the way to the end, and it is going to run all the way to completion really. Let's go down and do that. So we are going to say task 1 and call the coroutine. And I think we should put a separator here to be able to separate these things. And if we build and run, the build is going to be good. We can clear and run rooster. And we are going to see that the coroutine is going to run code after the coiled 30 line. We will see the message here, and we are going to see that generate numbers is ending. And we are going to return void. You see that code return was used implicitly by the compiler, and we see our return void method here called. You can see that right here, and this is the message we see. You see that the compiler has called the co-return operator implicitly. We don't have that operator in our generate numbers function, but we are seeing this co-return operator used here, and you need to be aware of this. Now, because the coroutine has run to completion now, if we ask it if it is done, it is going to tell us that it is done. We can copy this message here and put that below our resumption here. And if we build and run the program, let's do that. The build is good. We can clear and run rooster. We're going to see that now the coroutine is done. And this is really how we can use our coroutine to generate numbers lazily on the fly. You see that the numbers we need are generated at the point where we need them. For example, for the first time here, if we call task 1, we're going to go in our coroutine and co-yield the number that we need, and the coroutine is going to pause. This is what we mean when we say that numbers are going to be generated lazily as we need them throughout our loops in our C++ programs. This is the example of using the generate numbers coroutine here, but we can also try out our infinite number stream here. Now, to try this out, we're going to go in the main function and comment out what we had done before to be able to follow this easily. And we are going to set up another task. We're going to say auto task 2, and we're going to say infinite number stream. I think this is going to be our thing. And this is going to call the coroutine and pause before any statement is executed in our coroutine here. But if we call the function call operator on this guy, for example, let's do that. We're going to say stdc out and say value and say task 2. This is going to generate the first number from our infinite number stream, and we will see the number printed out. So what this is going to do, it is going to initialize value here. We're going to run the first iteration of the loop. We're going to say infinite number stream, and then we're going to co-yield the value and pause. We are going to co-yield the first element, and that's going to be 0 because that's our starting point here. And we're going to see 0 printed out on our terminal. Let's pass this through the compiler to see if this actually works. The build is good, so we can clear and run Rooster. We will see our value here, and we will see that it is 0, and everything is working as expected. I am going to take out this stdc out statement because it is going to confuse us. Let's try to build again. We're going to pass this through GCC. The build is good. We can clear and run Rooster, and we will see our value here. Now, if we want, we can even print 100 values in the main function here, and all we have to do is loop for 100 times. So for example, we can say for size ti, and we're going to start from 0. We're going to keep doing this as long as I is less than 100, and we're going to increment, and we're going to set up a pair of braces, and we're going to move the code here within our braces. And this is going to loop for 100 times, printing numbers. And this is going to do what we want. We will print numbers from 0 all the way to 99 because we're going to be looping for 100 times. Let's pass this through the compiler. And don't lose sight to the fact that the numbers are actually generated on the fly as we need them. So at each iteration, we will call our function call operator. That's going to resume the coroutine, and it is going to run up until it hits the next co-yield statement, and we are going to pause again and wait for the coroutine to be resumed and co-yield the next number. This is what we are using here. Let's pass this through the compiler again. The build is good. We can clear and run Rooster, and this is going to go from 0 all the way to 99, and this is what we want. If we want, we can even let this run infinitely. And one way to do this is to not put in a NAND case test here, and we're going to leave this part here empty, and this is going to cause for the loop to run indefinitely. We can do this. Let's pass this through the compiler. You're going to see that the build is good. We can clear and run Rooster, and this is going to run indefinitely. You see that we can wait for this maybe for 10 minutes, and it is going to keep running. We don't want to wait for that long, so I am going to Control C on this, and the program is going to end. And this is something you can do if you need this in your C++ program. And this is using our infinite number stream coroutine here. The last one here is going to generate numbers within a given range. So we can specify that, for example, we want numbers between 10 and 20, and we're going to be yielding between those numbers. And if we hit the end of the range, we're going to hit the end of the loop, and we are going to hit an implicit co-return statement, and we will see our return void method here called. Let's try to do that. And before we do, we will comment out what we just did here. We are going to go down and say that we want to use our range, and we will say auto task 3, and we will say equals, and we will put in our range coroutine. We're going to say that we want numbers between 0 and 25, and we will call task 3 here. This is going to call the function call operator. This is going to resume the coroutine, and at each iteration, as we resume the coroutine, we're going to co-yield the next value, and we will see it printed out in our main function here. We can pass this through the compiler as we always do and see if this actually works. The build is good. We can clear and run Rooster. This is going to run from 0 all the way to 23 because we are looping 23 times. But our range is going to go from 0 all the way to 25. Let's see the coroutine here. It is going to test and see if first is not different than the last. So if they happen to be the same, the test here is going to fail. So this is basically going to run from 0 all the way to 24. So let's pass 24 here as our endpoint, and we will try to build again with GCC. And if we clear and run Rooster, we will see that our code is done. And if we pass 25 here, we want to see our coroutine hit the endpoint and see our return void method called. This is what I am trying to get here. So let's clear and run Rooster. And we are running all the way to 24. Let's do 26 here and try to process the 25th number and see what we get. Okay, the build is good. We can clear and run Rooster. And now you see that at the 25th iteration, we're going to hit the end of the coroutine and our code is going to run to completion. I mean, the coroutine here is going to run to completion because it will generate numbers between first and last, but last is not going to be included in our range here. This is what I mean. And this is really how you can use our custom generator to generate numbers lazily on the fly as you need them. And this is really cool. This is one of the cool use cases for coroutines, generating numbers lazily on the fly if you happen to need them. And my guess is that this is the same thing IOTA is doing. If you watch the chapter on algorithms, you know that we have an algorithm called IOTA, which is going to generate a range of numbers. And this is probably using coroutines under the hood, but I am not sure of that. This is really all I had to share in this lecture. I hope you found it interesting. We are going to stop here in this one. In the next one, I will show you that we can actually achieve this without having to build our own coroutine type. And we are going to be using third-party libraries to really do the same thing like we are doing here. And that's going to ease the job you have to do. And sometimes you won't even have to know too much about the coroutine infrastructure because you won't be building your own coroutine types. So go ahead and finish up here and meet me in the next lecture.